This is a summary of the training presentation done in January based on laser, camera or RFiD. And the analogy I like to use is the law of the instrument, meaning that if all you have is a hammer, then everything is going to look like a nail. And luckily at SICK we have the technology to read all types of code, whether it's an RFiD code, a 2D code or a linear code. So the analogy of only having a hammer is a bit of a dig at Cognex, because all they have to offer is a vision system. One of the most important criteria to consider when looking at an application is to identify the cost of your customer's business problem. And it might be sending the wrong product to the customer, and therefore what the cost is to the customer to fix it. Or it could be a poor read rate from a CRV. We can identify the cost of the no read and see whether it's worth buying a better CRV or an ICR device, a vision system. So this is just a list of some of the examples. But the most important thing to do is to look at the return on investment to make sure the customer can afford our solution and that we're offering him a payback. This is particularly important with RFiD equipment. So always look at the cost of the customer's business problem and therefore the cost for us to fix it, and see what true savings we're offering him, therefore what return on investment he gets. So what system do you need? Well, there are several ways of describing a system. You could have a centralized system or you could have a decentralized system. A centralized system means that the information is held in a central computer and the barcode just carries a number. It then looks up that number into the central database to tell it what it is. A decentralized system lends itself more to RFiD, and that's where the information about the product is held on the product itself, and that can be rewritten to it. So for example, in the application down here you can see where we're maybe putting in dosage instructions of weed killers or pesticides onto plants, and we want to keep a record of each time it was changed or when something was done to it. And this means the information follows the item around. One consideration is how many tags you're going to need, and will you be able to show a return on investment, because what you have to remember is although the cost of tags could be as low as 5p, they probably won't be tested, therefore they're not going to be massively reliable. You might be able to get tags for 10p, though most of ours are around 50p if it's our cheapest paper tag. So the cost of tags is a significant cost. If using a barcode system, we must make sure that we print the barcode of a good quality. We don't really need a verifier, as long as we follow these rules, that the thin bar must equal the thin space, and the thick bar must equal the thick space, for example. The edges must be straight, the code should be good contrast, there should be no white show through, and the quiet zone should be 10 times the last bar. You can see we've got problems here with the quiet zone, and you see it's quite useful rather than look at the code to look at any of the human readable above it or the bearer bars, and you can see bits missing here which indicate that had there been a bar printed in this area, it wouldn't have scanned, it wouldn't have worked. So check the bearer bars, and another point is to not use red bars on a white background, because if you do, all you're going to do is delay the fault to somewhere further down the supply chain, because we might be able to read it by using an ICR, for example, with a green light, but the customer is just going to send it down to one of his clients only to find that it won't be read with a red laser light. When reading a 1D code with a vision system, you might have an oblong or rectangular shape of reading field of view, and it's important to make sure the code fits in the field of view. So it's important to check the cell size with code calc and check the field of view and the depth of field. Another critical thing is never use a 4-digit interleave 2 of 5 or a 4-digit code 39. They're very insecure, and if you do use a 4-digit interleave 2 of 5 code, then you'll find it can invent numbers just almost out of thin air or just on any highly printed media. Here's a couple of examples that have gone wrong. You can see here the bar that should be the last bars have actually been printed over into some other print media, and they're actually on a tear strip. So when this code is torn off, there will be bars right up to the end, but if that's put onto a plain white piece of paper, it won't have the start and stop sequence on it because it's part of the torn off strip. Sorry, that's the tear off strip. Likewise, in this example here, you can see that the barcode is too close to the scanner and overlapping its reading field, so the image won't be in the reading field at any one moment in time. When describing barcode orientations, it's important to use the right terminology. All of these diagrams are on the CodeCalc Weebly site, so you can describe them to a customer and copy and paste and include these in an email so you know that you're talking about the same reading orientation. So here are a few barcode mechanics. So imagine you've got a carton moving along the conveyor at 60 meters a minute. That's the same as 1 meter per second, or 1 millimeter per millisecond. If the scan frequency is 1 kilohertz, that's 1,000 times a second, and the conveyor is going at 1 meter per second, the travel is 1 millimeter per millisecond, or 1 millimeter per scan. So, for example, if the code is 20 millimeters and you're getting 1 millimeter per scan, the maximum theoretical number of scans would be 20. If the scan speed was half, then the maximum number of scans would be 10. If the speed was half, then of course it would then be doubled. So by using the basis of 60 meters a minute and 1,000 scans a second, you can very quickly in your head work out how many scans you're going to get through a barcode. Another point to watch out for is if you're reading a picket fence code on the leading edge of a box as it travels forwards, looking at an angle of 45 degrees, it's the old trigonometry question again. And the laser line is following the hypotenuse, this line here, which is the longer line. So if the box width is 250 millimeters and the height is 400 millimeters, that means that height there is 400 millimeters. Then the distance from this point going up the hypotenuse is going to be cos 45 times the height of 400 millimeters, which is 1.414 times 400, approximately 1.5. That means the distance we need from the scanner to read a code when it's on the very top of the box has got to have a width, as you can see here, a box width of 250 millimeters. So that's 250 millimeters there. I've got to have 250 millimeters laser line. So you can see, for example, if we said we started around this point at roughly 300 millimeters distance, we've got roughly 300 millimeters laser line. And as we already calculated, I need 600 millimeters along the hypotenuse. So from this point, 300 millimeters, I need to go out to 900 millimeters so that I can get my correct depth of field to give me the sweep from a code that would be at the very bottom of the box right the way up to the top. So that tells me the distance from the bottom of the box to effectively the top of the box where we'd stop scanning, where we get a scan width of 250 millimeters. But we have to allow obviously a little bit of room for the box to get underneath the scanner, which in truth we will have. If we're mounting it approximately 300 millimeters away, we're going to have enough clearance for the box to go under the scanner. Quite often I get asked, what's the benefit of going from the 4 series to the 6 series? Well, apart from the obvious one that we have no choice, you can see here if you have a partially damaged code, you can see the difference here going from the 430 to the CLV 621 or the CLV 630. You can see there's a big difference in performance. If we then go to a more severely damaged code, you can see here with the CLV 430 we would have got 590 no reads. With the CLV 621 we got 492 no reads, but the CLV 630, which has a more advanced smart in it, only gave 62 no reads. And as we know, no reads cost money, so if we can eliminate them, we save the customer money. But don't forget, if the whole bar is missing, so if any one of these bars is missing in its entirety, the code can't be scanned. You can't read it. You can't read it with a hand scanner or a fixed scanner. This particular scanner here, code here, you can read with a line scanner as long as it moves through the laser beam, but a hand scanner won't read this because at any one point you're trying to read with a hand scanner, it's got barcodes missing. So for 2D printing, the important thing to look for is that we're working with an ECC 200 specification, and the quickest way to identify that is to look for the white dot in the top right hand corner of the code. This one here doesn't have it, and this one is therefore not ECC 200 and therefore can't be scanned with our equipment. So for printing you need one module all the way around the code, so that's one module all the way around the code as a quiet zone. The finder pattern must be intact, that's this part here, although we can put in a configuration in the scanner to tell it to tolerate damaged finder patterns, but it's good to go for good practice and try and keep them decent. One other point, the DPM decoder is actually designed more for dot peen, or what we call pin stamp. So if you're laser marking a code, then the marks are going to be square dots rather than round dots. Then you'll find the Lector Pros just as good at reading these. So for reading with a vision system, obviously check the field of view to make sure what you want to look at will fit in it. You can see here this code wouldn't work, it's too big for the reading window we've got. We need to check the depth of field and check the frame rate versus the speed. And what we're looking for when you configure it is 2 or 3 pixels on the reader. So when you're working with the diagnostics on SOPAS, you'll notice it'll tell you how many pixels wide by how many pixels tall. So how many pixels tall that way and how many pixels wide each cell is, or each module of the barcode is. This is just a quick representation of the range going from our Sylvie 610s through to the 650s and then up to the Sylvie 690s. And a little organogram here showing the features that they have, which is quite useful. And then the 2D solutions, there are 5 different variants, but in reality all you need to remember is the Professional and the Eco. Big difference with the Eco, you notice there's a couple of lights missing. The Eco comes only with a cable and using USB to get the image, whereas the Professional gives you USB and it gives you the Ethernet. If you're working with a high-speed application or with a DPM or with an OCR, you'll be speaking to Neil or myself. So I would suggest you focus mostly on these 2 units and their performance capabilities. And you're probably aware of the Lector 640, 650 range and the fact that we've got a Lector 630 coming out later this year. And once again, for applications using these, then give myself or Neil a call. Our RFiD solutions are predominantly using these devices here, which are HF. So these are devices that work at relatively close range on tags that can be mounted on metal, but HF solutions don't like metal because the metal attenuates the signal, whereas they can cope with water. Conversely, UHF, which are these devices here, UHF don't work well with water, but they can cope with metal. And once again, you can get on metal tags, and generally you get a much longer range with the UHF systems. But if you're talking about an RFiD system, then please give me a call. So with RFiD, obviously the tag quality is important, but most important is the environment, checking the mounting of the tag and how much data you need to write into it, whether it's a captive or distributed, or whether that means whether the tag stays in the factory or goes out to the big wide world, and whether it's a centralized or decentralized system. And in terms of reading, we need to know the range of the tag to the interrogator, which always must be kept as close as possible, despite the fact the datasheets show that it works over a long range. We don't want any overreach where we read data from the wrong tag. And we need to know the distance between consecutive tags to make sure that we're not reading the wrong tag, and the distance between interrogators so we don't fill the whole place full of too much UHF, and that would cause problems of getting it to operate in the time that we need. So general principles, RFiD is very good in dirty or harsh environments, or where you need to write data to the tag, especially where there's no line of sight, but important to check the return on investment. Vision or camera systems like the Matrix and the line scanner work very well with poor contrast or low aspect ratio or omnidirectional, and you can see here this code is a very low aspect ratio. That means it's not very tall, but it's very long. So ideally to read that one we would use a vision system, an ICR. And lasers work well where you've got a large depth of field, a wide reading area, and they tend to be lower cost. So if the barcode is very structured, good contrast, and fairly large size, but you need a large depth of field, the laser is often the most economical method. So here's a table you can see comparing the different principles. So looking at the costs of the labels, here you can see roughly 5 euro cent. I would say that's quite optimistic, and it would not be a very good tag. Few important things: obviously sensitivity to ambient light, no influence with RFiD, very low with laser, and low to medium with a vision system. Obviously a vision system uses light, so there has to be some impact. The way a laser reader works, it sends a light spot over the code at high speed, and that's why it looks like a laser line. And the way that it operates, it decodes the code as the laser spot goes through the code in real time. That means that as soon as it goes through, it's going to find a quiet zone that it's looking for and then get pulses through from the barcode as it travels through. And once it's got its fixed number of pulses, because if you told it what code type and what code length you're looking for, it would know how many bars it should be finding. So it can often cope with a quiet zone problem on lead out, whereas it can't on lead in. So if it's going from top to bottom, here you need the quiet zone, but here if it's infringed or damaged, it can still scan until this code is turned through 180 degrees. And then you'll find that the damaged quiet zone is on the lead in and it won't read the code. It's one of the most common faults with the barcode system is the quiet zone or missing bars. So they'll print a code that looks like a barcode, but the last bar or two are missing, and it couldn't ever scan. Here you can see what a matrix camera looks like. I'm sure you're all aware of this, but the idea is we need to make sure that the dots or the pixels are covered by a dot of the barcode. So either the barcode, or you can see here a 2D code, needs to cover several pixels so that we can get a successful decode. And it's called a matrix for obvious reasons. We have a matrix of pixels. Here you can see an average price laser reader, and you can see it's actually working from approximately 200 millimeters out to 1.6 meters on a 0.5 millimeter code. If we overlay it with the reading of a matrix camera with a 0.3 mil code, you can see it works with a smaller resolution over a longer range, but the read height is significantly smaller. We could improve this read height by putting on a different lens, but then it would have to be a much shorter depth of field. A line scan camera has a different principle. It has 1 pixel wide by maybe 6,000 or 8,000 pixels across, and it uses effectively a shift register to take multiple images of any item that goes past, and then you rebuild them together to give you this sort of an image. And you can see the performance from these is absolutely superb. So this is a vision system but using a line scan camera, and this is the ICR 880 or ICR 890. Here you can see a comparison between the CRB 690 now, our top-end laser reader, versus the line scan camera, and you can see the reading range is significantly more on a smaller cell size. So this works out with a cell size of 0.3, whereas we're working out to roughly 2.1 meters on a 0.5 mil on the laser reader. So we get a much larger range, but not quite such a wide field of view. Here we've got a 1200 millimeter field of view with the laser scanner, whereas with the line scan camera, the maximum, this one, is going out to 1 meter. But note, we have to start at 1.4 meters distance, whereas with a laser reader we can start reading approximately 500 millimeters away. So here are a few reading applications. You can see here we need no depth of field. We've got a very poor contrast code here, so the laser reader wouldn't read this, but the matrix scanner would. You can see it's ideal for this application where we've got labels and poor contrast, and also we've got snuck in there a 2D code too. This application is very simple, reading tote boxes, so either the matrix reader or the laser would work. The line scan camera would be too expensive and it wouldn't really offer any payback. On tilt tray reading on the leading edge of the box, the laser reader would work. The matrix reader might struggle a little bit, and the problem with the line scan camera is the cost. For reading barcodes on a pallet, actually the matrix reader could do this if it was a well-defined position that the barcode was going to be in, but typically on pallets there could be quite a wide range on read height. You can see here we've got a read height of 1.2 meters, and we need a reasonable size depth of field. So once again it points more to laser. Looking at the courier and express parcel market, then obviously laser omnis are much better, or the line scan camera come into their own. Matrix readers can be made to read these, but the truth is they really suffer. You can see all the problems they have. However, Cognex are trying to make theirs do this sort of application. To our knowledge, they still haven't succeeded. And obviously airport reading systems, the lasers really do come into their own here. This is the tyre application, and you can see everything works here. Truthfully, I think that the matrix reader works better on the tyre application because they quite often produce barcodes where they've got poor quiet zones. And this is actually being read here by a matrix reader, and it's a much better solution. So this is a decision matrix. You can pause this to have a look at it yourself. Hopefully you agree with the smiley faces, but it should give you an idea as to which technology is best for what type of application. There are a few undeniable facts that we need to get across to our customer, and that is there is no single one right technology. There's no silver bullet. It totally depends on the customer's application. And there's no one right reading device, obviously, but there is a right reader for the customer's business. And the important thing is that we don't push a product. We look for a solution to the customer's business problem, not just trying to sell him to solve the problem he's presented. So we're going to offer either RFiD, 2D readers, laser readers or vision to solve his business problem. Unlike Cognex, where their solution is to try and push a vision system every time. So best talk to a vendor with a full toolbox. I don't mean that they're a drumstick short of a picnic necessarily. I'm sure they're very bright, but we have a better toolbox to offer. So don't forget where you can get information from. So there's the mobile app for CodeCalc to help you calculate the cell size. You can use these links here, or the bit.ly download, or if you've got an Android phone, scan one of these 2D codes. So just to summarize, if we have an application like this here with a tote box where we've got no depth of field, the speed is very slow, the code is in a very exact position, the cell size is 0.5 millimeters, and the code is small, it's only 30 millimeters long. If the contrast is low, we would use an ICR to read it. If it's a low aspect ratio, once again an ICR, you can imagine this laser trying to be aligned to look at that code. If the barcodes are in any orientation, we'd use the ICR because it's omnidirectional. And if it's an easy barcode like this one here, then we would use a laser reader, therefore CLV. So finally, just to recap, when you want to look at the code type, check the beginning bar and the end bar and see if it's a thick one. If it's a thick one and then check the pattern, it's likely to be one of these codes, code 128. Look for code 39, which would go thin bar, thick space, thin bar, and then thick bar, thin space, thin bar, or ITF that looks similar to 39, look at these here, but notice the thin bar, thin space, thin bar compared to the thin bar, thick space, thin bar. EAN 128 looks like the beginning of a code ITF or Interlude 2.5, but the last bars are different. And if you can't identify what the code is, have a look and see if the last bars are even printed. Some people have a habit of not printing the entire code, so you might have a bar missing at the beginning or at the end, and they're convinced that it's a genuine barcode. So always have a good look at the start and stop sequence and make sure that they make sense. Okay, that's it. I hope that was helpful and a useful recap for you. Thank you. Cheers.